Okay, hi guys. This is the first of a series of four specific Phanerozoic Earth history PowerPoints. So this material is largely from your textbook. So again, continue to read your textbook as you go. Listening to my lectures is really helpful. Sitting here and reading the PowerPoints is not going to help much because some of them are just pictures. And a lot of them don't have context. You know, some of the pictures will be pretty complicated. So if you're seeing something you don't understand, please go ahead and turn on my lecture or dig into the textbook, which will have a lot more detail. The PowerPoints may be good things to have on hand as you're doing the exam, but really the textbook will be there anyway. But you know, between the textbook and the lectures, I think we'll get you there. So it sounds like we've got a lot more to go. That's not really the case because we only have to go through about 10% of the remainder of Earth history. So if you were taking a prehistoric life course, which I teach in the fall, it's Geology 125, we will focus much more on the life of these different time periods. And that's one of the, well, in my opinion, one of the most important things going on is what's happening to biology. But you know, because we're talking about the history of the Earth, one of the big things we're focusing on instead is plate tectonics. And as we're doing that, we're looking at how continents have changed over time, how supercontinents have been sutured together and then been pushed, extended and shoved apart. We're looking at mountains being built and then eroded away. We're looking at sea levels rise and cover, you know, huge sections of the continent and then being dropped again. So continents, there's much more continental mass exposed. We're looking at ice ages. We're looking at life as well, extinction events, new evolution and radiation of life. So there's a lot of cool things going on. But remember, we're only looking at the last 10, 12% of Earth history now as we start at the beginning of the Cambrian, about 540 million years ago. So here's a nice geologic time scale, and again, all this purple stuff at the bottom called the Precambrian. The wavy line here is to indicate that none of this is to scale with any of this stuff. So we're going from 542 million years ago all the way down to 4.6 billion. So yeah, almost 10% or 90% of the way through Earth history by the time we get to the Cambrian. And this is going to be the Phanerozoic eon. So that's what we're concentrating on now between, between now and the end of the semester is one single eon. We've already covered several, the Hadean, the Archean, and the Proterozoic, and those were by far, especially the Proterozoic, the largest ones. We're spanning a time period from, it covers over 2 billion years of time in the Proterozoic. So all that is just referred to as Precambrian time, now that we're in the Cambrian period and starting onto the Phanerozoic eon. So today I'm going to look at the first half of the Paleozoic. We're looking at the Cambrian, the Ordovician, and the Silurian periods. And then we'll do the Devonian, Carboniferous, and Permian next time. Then we have a lecture of the Mesozoic and then a lecture over the Cenozoic. And none of this is to scale. So it looks like the Cenozoic should be really big. It's not. It's only the last 66 million years. To put that in perspective, the whole Triassic, Jurassic, and Cretaceous of the Mesozoic span, almost 200 million years. So this blue chunk should actually be about 3 times the height, 3 times the size of the pink chunk. So, we do that so we can zoom in and see these different epochs, because it is true that we know more about more recent Earth history. There's more details we can iron out. We can tell a big difference, for instance, between the Oligocene and the Miocene and stuff like that, that we can't really do as we get further back in time. So we are spending some time with the Cenozoic later on, but that doesn't mean that it covers a vast amount of time. It just means we have more information on it than on any of the other periods. So that's why these numbers are kind of squished. So if we were to look at it as to scale, the Cenozoic would be like teeny tiny, the Mesozoic would be pretty big, Paleozoic would be huge, the whole Precambrian would be, immense. So again, we're just kind of, trying to wrap our heads around the immensity of Earth history, and that's not easy to do. So we are talking a lot about supercontinents, and so we're starting out with the very beginning of the Cambrian period, right before that, which was about 542 million years ago. At 550 million years ago, we have a supercontinent come together called Pannotia. We've already had a supercontinent that we talked about. Hopefully you watched the Appalachian lecture already, because that one spans a huge period of time and has 4 major collisions that have to do with supercontinents. And during that time, we are constructing the Appalachian Mountains. So that's a really good sense of this one location on Earth. Well, sorta. It's spread apart to many places now, but there's one place on Earth that tells us a vast story that involves a big chunk of the history of our planet. So now we're just kind of going chronological, and the Appalachians will come back periodically. The Appalachians began with a collision of a supercontinent called Rodinia about 750 million years ago, or about 1 billion years ago. Now here we are with another supercontinent called Pannotia. So Pannotia is going to be oriented around the South Pole, and that's what this is looking at. So I'm going to take a little red pen here and put a little dot there. This is the South Pole. So we're not looking at a map the way we normally do, where the equator's in the middle and the poles are at the top. When all the continents are oriented around one pole, then we rotate the Earth so that we can see better what's happening. If you were to look at it from the side, you wouldn't see a whole heck of a lot. So we have a lot of continental mass right on the South Pole. We're very close to it. So that's Pannotia. And it's going to begin to break apart. And as it's breaking apart and these continents are beginning to move around, we are going to get closer to forming Pangaea, but we won't get to that story quite yet. That's going to be a while. So Pannotia is the continent we're talking about. So a lot of the history of the Earth through the early Paleozoic is all about those cratons, which had been built up, those kind of basic basement parts of the of each major continent. And so we have 6 major continents throughout the Paleozoic, the early Paleozoic. So China is one of these. We have Baltica, Gondwana, which is going to be the southern continents like South America, Africa, Antarctica is going to be in there. So is Australia. We just call all of those Gondwana. And we've got a few others. Ours here in North America, we are on the supercontinent of Laurentia. So that's where we are. So these are the 6 major continents. Again, world's looking very, very different 500 some million years ago than it does today. The continents are even different names because any other parts just build up to make up one of these continents, or they're just either not created yet or not small enough to really count as a continent. So each continent basically had 2 major parts: the pretty stable Proterozoic basement rock or craton, and then we have deposition occurring over top of that. So a pyric, that means seas that are on top of a continent. We don't really have any around today because sea level is relatively low today, but we have many times in the past. We're going to see some big trends of sea level rise, depositing miles and miles of sediment on top of the continent, and then sea level declining, sea level decreasing, and that rock that was deposited is now being eroded away, or it's exposed at least. And so we have seas rising, which is transgression, and seas falling, which is regression. So this is going to make a history, this is going to record what's happening throughout much of the Paleozoic. So even though, we don't really have glaciers so much during this time, don't really have significant ice sheets, we do have sea level fluctuating a lot. Okay, and we also have mountain building, and a lot of that's going to be the Appalachians and some other mountains that we'll get into as well. So these are 2 major, episodes that occur to every continent. We'll have mountains being built, and mountains are not just building skyward, they're also where we have land masses kind of glommed on to the side of a continent, building it up laterally as well and making that continent larger and larger. Same thing with sedimentation from rising seas. We're building onto that continent further and further out, not just vertically, though the vertical movement will make a big, big difference too. Okay, so we have a few things going on here. This is looking at North America about 550 million years ago. So we're looking at the major cratonic structures and mobile belts of North America during the Paleozoic. So in North America, there are 4 major mobile belts. We're looking at the Franklin, the Cordilleran, here's the Cordilleran right here. This is going to be kind of the baby part of the Rockies, so the very first thrust of the Rockies. By the way, the Appalachians have already been, have been risen up. The Rockies are far younger than the Appalachians. The Ouachita, which is also part of the southern Appalachians that end up over here into Arkansas. And of course the Appalachians, which are going to continue to build, but are at this point already very tall mountain systems. So check out what else is going on. Aside from just those mountain belts, well, this pink part here, the Canadian Shield, that is showing us the craton, the stable basement rock, the interior, the kind of the original part of our continent, and everything else is being added to it. So we are building up mountains over here with this. That's what the blue is representing, is the Cordilleran, which is beginning to form Alaska. We're globbing the Appalachians onto this as well, so we're extending outward our continental mass of North America. And we're also depositing a whole bunch of sedimentary rock too. So for example, here in the Cincinnati area, we have our Ordovician aged limestones being deposited pretty soon. It'll be about 450 million year old rock. So that's going on. We have rocks that make up the Michigan Basin. We have a whole lot of the Permian Basin. That's going to be later, much later. But we're looking at all these different depositional environments happening too while we have mountain building going on. So we're building laterally onto continents as well as vertically, both from sediment and from mountain building. So through the late Cambrian, this is what the Earth is looking like. As with all the Paleozoic, late Cambrian paleogeography excuse me, is primarily based on data from structural relationships. So we're looking at rock deformational features like anticlines, which are kind of folds upwards, synclines, which are folds downwards. If those are not too familiar with you, then for you, that's okay. But that's how we determine the history of mountain building that has gone on. Any sedimentary rocks that are climate sensitive, so things like red beds, which form from rivers coursing through an otherwise pretty dry area like a desert. Sedimentary rocks like evaporites, remember rock salt? That tends to tell us that this was a desert, very dry. Coal is a good example of a tropical swamp. There are glaciers that leave behind, very specific kinds of sediment that indicate, okay, this place was covered by ice. So many sedimentary rocks tell us about different climate zones, and that's how we piece together that this part of Laurentia, which is North America, I'll just put NA here to kind of show what's going on, that part of it was on the equator. And we know that this part of Siberia, for instance, was at 30 degrees south, which is desert latitudes, because there's a lot of salt here in this area, for instance. So we're also looking at fossils too, to kind of determine the paleogeographic positions of the continents. During the late Ordovician, now this is a time that's very special to us because I'm going to take a red dot and put it right here on Cincinnati. Cincinnati would have been covered by a tropical shallow sea, so relatively close to the equator, and Laurentia would continue to move closer to the equator throughout the rest of the Ordovician and the next period, the Silurian. And if you saw the Appalachian PowerPoint, one of the things that you know that happens is that Baltica and Avalonia, this is going to end up being part of England later on, these are going to collide with Laurentia, closing the Iapetus Sea and suturing onto Laurentia, building not the Taconic orogeny, because we already have that, but the Acadian orogeny of the Appalachians, the third orogeny that would form the Appalachians. So one more to go after this happens, but that's what's going on during the Ordovician. That's starting to happen. Gondwana is moving southward, so after Panotia it had moved, but now is going back down south and actually crosses the South Pole. And some continents, like Antarctica, is going to, are going to remain down there. We also know that during the late Ordovician, there was glaciation that caused a mass extinction event that we see evidence for in our local rocks, which is pretty cool. But we'll get into that more with prehistoric life, or my Geology 110 class gets into that just a little bit. But we know that there were some glaciers occurring, and this is the first time ice grew on the planet since complex life evolved. During the early Ordovician Avalonia separates from Gondwana and is moving northeastward, and again is going to collide with Laurentia, and this is going to end up being, part of England. So we see a lot of evidence for this orogeny occurring here. And this is the Caledonia, that's the old Roman word for Scotland. So this is going to be Scotland, this is going to be England. Yeah, they were sutured together. They were apart for a long time, sutured together at the same time that the Appalachians are being formed here. And we see evidence of the tectonic orogeny in New England. That's a good place to see evidence of that. Our rocks here, a little bit closer, like in North Carolina, are a little older. And show the more ancient orogenies, like the Grenville orogeny. Okay, then in the Middle Silurian, so we're moving on with time a little bit here. During the Silurian, Baltica and Avalonia are going to collide with Laurentia, finally creating the Caledonian orogeny, which is going to form the Highlands of Scotland, and the Acadian orogeny, which is going to form our Appalachians here. So we have a lot of things moving on in the south as well. Siberia and Kazakhstania are moving from their southern, very tropical position. Oh, here we go, Kazakhstania, in the Cambrian to becoming more northerly and becoming more temperate. And again, so we could tell that these islands here, and China as well, went from being equatorial, which well, no swamps at this point because really no plants at this point, but they're becoming more temperate. And again, sedimentary rocks can help us determine that sort of thing, which is pretty cool. So anyway, it's just a little taste of what's going on as far as our plates throughout this lecture. Kind of continuing here. Get into a kind of a crazy concept that if you took said strat, I know some of you guys did, and some of you guys never will. So we have a mix of people here, so I wanted to go ahead and introduce this concept. The study basically of what happens when sea levels rise and sea levels fall. And that's sequence stratigraphy. So we're looking at a whole sequence of, or a whole package of sediments, not just saying, oh, sea level was high here, oh, sea level dropped, but actually seeing, maybe the rate at which sea level rose or fell, the types of sediments that are deposited, all sorts of different things. And that's not just telling us about that sedimentary rock, it's telling us about much bigger things like global climate changes, glaciation events, but there's other things that cause continents to rise, or cause relative sea level to appear to rise and fall. And one of those is that continents can also rise and fall. Remember, continents are floating in the mantle of the earth. Okay, so as they get a lot of sediment being built up, either from sea level rise, which is going to create a bunch of sedimentation on that continent, or from mountain building, so we're going from a flat plain to getting this huge mountain belt that could be, a mile or more tall. That's a lot of weight. So now we have a very heavy but very thick structure sitting in the mantle. That's what's floating in. So it can begin to sink. And as mountains erode, continental material can begin to rise. So the continent itself also moves. It's a much slower rate than climate causing sea level to rise and fall, but it definitely happens. So we're going to look at what are called cratonic sequences and sea level sequences as well. A big reason why sequence stratigraphy is a big deal for geologists is to locate things like petroleum. So a lot of the sea level rise and fall will help us to determine where shallow sea deposits are. And shallow sea deposits are generally where petroleum is found. So a little bit about how to read this. This is different than the one in your textbook because I like this one better. The tan is showing you continental material. So here we are at the oldest part. I'm going to put O here for old. So this tan part is showing you the exposed land, and we're only looking at the sequences on North America here. The blue is showing you where the oceans are more dominant. So for instance, we have a lot of continental material here at the early Cambrian, but we see, and there's a little bit of back and forth because sea level just is never steady. It goes, it ebbs and flows a bit over, few million years. You have a pretty long time spans. And so what's happening throughout this area is sea level is rising. So we're losing exposed continental material, and we have oceans covering up more and more of the continents. Here, by the time we get to the very early Ordovician, there's really no North American landmass at all. It's all covered by the sea. So this can help us understand that we are seeing maybe a very warm climate. Maybe we're seeing a continent that doesn't have a lot of mountains on it yet, so it's able to be buried. So that's pretty helpful. And what this tan stuff is representing too is no sediments being preserved. And they can't because it's exposed. So we generally have sedimentation occurring when we have sea level relatively high. There's not a whole lot of terrestrial environments that will deposit vast sheets of sediment. It's oceans that do that. Through the Ordovician, sea level, or relative sea level drops again, and we have more of the continental material being exposed, but sea level continues to rise, and so on. So we see a lot of, kind of ebb and flow in each of these sequences. We'll talk about a few of these. We'll talk about the Sauk, which is right behind me, and the Tippecanoe sequence, and some of these other ones later on, because we're going all the way to modern times, which, by the way, sea level is pretty darn low today, relatively, because we have glaciers on our planet. So during this time, we're not seeing a whole lot of, sea on top of the continent. So anyway, it gives us a little bit of a taste of what we're in for as we look at how sea level has fluctuated. Now, this one is from your textbook. I like this image because it's not just showing us what's happening to sea level, it's also showing us the mountain building episodes here too, both related to, here's the east, so the Appalachian and Ouachitas, Ouachitas of which are exposed in Arkansas now, and the Cordillera, which is the Rockies. So I'll put W there for west. So we're kind of looking across North America from east to west. And the brown is showing us where we've had more of North America exposed to the air, and the white is representing sea level. So we've had more of it, buried by the sea, covered by the sea. So we're looking at pretty major transgressive, regressive cycles, which means sea level rise, sea level fall, and we're looking at big mountain building events as well. So we have, Cordillera on the left, Appalachians on the right. So the sedimentary rock record of North America, and all continents, but we're just talking about North America here, is divided into 6 cratonic sequences. Transgressive phases are usually covered by pretty well-preserved younger sediments. Regressive, or sea level drop, phases are ending with an unconformity. And again, back to our geologic time lecture back in February, perhaps January maybe, an unconformity is a gap in geologic time where we don't really see a record of that happening. Sea level drops don't always tend to show us good evidence as sea level rises. So these 6 unconformities extend across various sedimentary basins of the North American craton and into mobile belts along the cratonic margin, or the edge of the craton. So this is going to extend all the way to where we have mountain building going on. Some of these transgressions and regressions can be connected to global cycles too. So not all of them, North America is kind of doing its own thing in a way, but when they can be related to what's happening on other continents, that tells us more is going on than just the continent shifting. We're looking at sea level rises and falls due to climate changes, because those tend to be more global. All right, anyway, so a couple of these. First one is called the Sauk sequence, and this is going to be the first time where sea level really rises dramatically up onto the North American continent. So we get a lot of marine sediments being dumped on places near the Appalachians and the Cordilleran border, so the east and the west, again, like we saw. And then through the early part of the Ordovician, we actually have a very warm tropical climate, and so we have erosion taking place. So tropical means rain. Rain is beating up the sediment, it's beating up the rock that's exposed here now, and it is going to carry it away back down to the oceans. So lots of rain means lots of erosion. Rainforest soils are some of the poorest on Earth for this very reason. Once we start getting a lot of rain, minerals, all that stuff is gone. The reason why rainforest soils can be kind of rich is because we have trees and all sorts of vegetation holding those nutrients back. Well, check it out, early Ordovician, no plants on land yet. We might be starting to deal it. Actually, we're not even going to see the beginnings of any kind of mossy type of material until the Silurian period. There's nothing on land to hold back any soil, so that's being washed away. So we end up getting a lot of erosion, and we have that sediment being dumped in the sea instead. So this is what North America is looking like during the Cambrian again. So we are pretty close to the equator. The red line is referring to the equator, and it's not that the equator used to run from like north to south. It's that, check it out, we kind of have this outline of the Great Lakes here, which is kind of silly because they're not even thought of yet. You got Florida. The reason why they do that is because they want to have North America in the same position that you guys are accustomed to seeing it, right? What they would do, and what I've seen other maps do too, wouldn't be too bad, is to actually rotate North America and keep the equator horizontal like it actually is, right? Well, anyway, so they just made it so it looks a little bit more recognizable for us as North America. But so here's the exposure of the Canadian Shield during the Cambrian. We have a bunch of sediment washing off of the Canadian Shield here on our tropical climate, where we have sediment being washed away because of all this rain happening on the equator, as today. So we're washing a lot of that sediment here, creating a sandy bottom of the sea. And then we have a carbonate bottom, and this is going to form a lot of the limestone that we see in much of the Midwest and further out west as well. And we do have some mountain building going on here. There's going to be part of the Ouachitas, and here's our Ouachita Appalachian Mountain Belt as well. We're starting to form the Cordilleras a bit, but they're not doing a whole lot. So we go from land to sand to limestone to shale, mud. So different sedimentary rocks, again, tell us quite a bit about different sea levels. So we basically have just the Canadian Shield and a few little islands here down in the south exposed during this time period. So we tend to have quite a bit of sedimentary rock from the Cambrian in North America. Except it's then covered by, younger sediments. So we actually don't see directly, I don't think hardly any, Cambrian sediment here in Kentucky. We see Ordovician instead, which is a little younger. We'll see that in a bit. So one of your essay questions you may choose to do is all about the Grand Canyon. And the Grand Canyon is going to cover a few different time periods here. But I want to talk about, kind of get into the complexity of it a bit. Here at the base, we have the Vishnu schist, which is Precambrian and dates to, I believe, about 3.5 million, or sorry, that's not very old at all, 3.5 billion years in age here with our Vishnu schist. And then we have, basically what happened is the boring billion, or the great unconformity, where we have this huge gap in geologic time where not a whole lot was going on. And then the Tapete sandstone is dumped on top during the Cambrian, so about 540 million years old. So we have a huge gap in geologic time between when the schist was formed as a metamorphic rock, probably deep in a mountain belt somewhere, and between when the Tapete sandstone was deposited on top. And we have our shale, limestone, the same rocks we were just seeing happened during the Cambrian from, all that ocean being very high, covering the craton. And we have our sandstone, we have shale, we've got limestone. Those are our offshore or marine sedimentary rocks we expect. Then during the Mississippian, which will be a very special period that we're missing the Cambrian and the Silurian and the Devonian. So this is another unconformity called a disconformity because it's between two parallel beds of sedimentary rock. And the Mississippian was a time period that saw a lot of carbonate production. So we have more limestone, not surprisingly. And then we go up through these other time periods that we will get into in the next lecture. But so anyway, that's a little bit about what's happening during we have some of those Cambrian rocks in in the Grand Canyon. So the Grand Canyon is a really great example how every single lecture I have, the Proterozoic, different parts of the Proterozoic actually are different parts of the Precambrian, the early Paleozoic, the late Paleozoic, the Mesozoic, and then finally the Cenozoic all have a piece of the puzzle of the Grand Canyon. And you could probably say this about the Appalachians too, but the Grand Canyon is where we can have some very nice exposures without a whole lot of vegetation covering all this stuff. So the rocks of the Grand Canyon preserve more than 1 billion years of Earth history, much more than that, including periods of mountain building and erosion, as well as periods of sea level rise, transgressions, and sea level fall, regressions of shallow seas over the area. So here in the Cambrian, we have a very excellent model of marine sediment deposition during a sea level rise. So we have a pretty stable marine environment, and sea level remained relatively constant while these clastic materials were deposited near shore and finer grained carbonates deposited a little bit further offshore and away from that source of the clastic or sandy sediments. So lots of good evidence of what's happening in the Cambrian for all of North America here in the Grand Canyon. So here's some other Cambrian rocks of the Grand Canyon, or actually just getting into more detail there. So here's our big non-conformity, and at the top was a disconformity, but we'll deal with that later on. And so we're looking at this from a side view where we're looking at sequence stratigraphy, and we kind of have this pattern of sea level rise during this time period because sandstone tends to be a more closer, a more near shore environment. So that's going to be like the beach and just a few hundred or so miles off the beach. Then we start to get into shale, and then we can start to get into carbonates. So this is giving us a good record throughout geologic time, throughout the Cambrian period, of sea level rise. And so that's really cool. If we had the opposite, if we had limestone, then mudstone, then sandstone, that would tell us we had a sea level drop. But this gives us an idea of a sea level rise throughout pretty much the entire Cambrian. So this is the Sauk, a part of the Sauk sequence going on here. And before this, the region was mostly above sea level, which is why this metamorphic rock here was heavily eroded, and so these new sediments were able to be dumped right on top of this very, very old metamorphic stuff. Okay, and we'll get into more of that a little bit later. So this is kind of a block diagram of some rocks that we see exposed in the Grand Canyon as well. Let's see what else. Okay, so the Tapete sandstone is going to represent kind of the very beginnings of that sea level rise. And then we are getting into the Bright Angel shale, which is going to be, more sea level rise. And finally, the Muav limestone, which is where sea level reached its highest point before we have the Ordovician occurring. So, all right, I think that's probably good for the Grand Canyon. Okay, and we're seeing similar things in the Appalachians as well. So here's a block diagram from the craton that's on the interior or westward side of the Appalachian belt. This is showing 3 major Cambrian facies, or bodies of rock from the Cambrian, and also showing us what's happening over time. We're looking at also carbonates forming here at the top, more sandy stuff down here at the bottom. So this is also showing us sea level rise, not surprisingly, because during about the same time, we have sea level rise in the west, as we just saw. This picture here is an outcrop at the Wisconsin Dells that's showing us an area of cross-bedded upper Cambrian sandstone. So we're starting to drop sea level in order to form sandstone. So this is very, very old stuff, older than anything that we have in the Cincinnati area, exposed in a nice, very beautiful area that I've heard, I haven't been, of Wisconsin. So we have some other evidence of the Sauk sequence besides just in the Grand Canyon. During the Ordovician, this is kind of our favorite because here we are near the equator, and Cincinnati is going to be right here. Ooh, we're underwater. Well, that's why we have so many shales and limestone here in the Cincinnati area that are covered, or well, That's why we have so many shales and limestone, I'm sorry, because we were under the sea, and you generally only tend to get a lot of deposition of sediments if you're in a marine environment. So if it wasn't for that, I don't know what kind of rock we'd have here. I guess it'd be all the way down to Cambrian. But we have all these little seashell fossils. We do have some bits of coral, but coral was just kind of beginning to evolve during the Ordovician period. We have all these little seashells, and they're all typical of animals that would live like in a Bahamas tropical style shallow sea. So that's how we know, because of the fossils here and probably in your backyard, that's how we know that we were close to the equator here in Cincinnati and we were covered by a shallow sea. The only landmass poking up in North America are some parts of the stable interior craton here making up the Canadian Shield. And parts of the Appalachians that are continuing to build during this time. So while we have sediment being dumped here in Kentucky and Cincinnati area, that's all limestone and kind of a nice Bahamas style sediment, the Appalachians are continuing to rise skyward. And so eventually, as they become more and more eroded, we're going to expect whatever sediment comes off of them, sand, to be dumped on top of this limestone. That's exactly what's going to happen, but it'll be a little ways. So we've got a little time before that. That'll happen about 300 million years ago. So we are looking at, let's see. Okay, so we have this very tropical environment going on here, and eventually, though, we end up with an unconformity that's going to represent the boundary between the Sauk and the next sequence called the Tippecanoe. So the Tippecanoe Sea is also where we have a transgressive sequence, so we have sea level rising. Same thing, we have our kind of clastic environments, more of a limestone environment. Whenever we go from clastics to limestone, it means sea level is rising. Whenever we have the opposite, then generally it means sea level is falling. So we're going to see more evidence of this over parts of the Midwest like Iowa and Oklahoma. So we have our stable craton, but again, all this metamorphic material, some of it is becoming metamorphosed, but we have an unconformity here as we have new sedimentation depositing on top that is far younger than this Cambrian material down here. So this is not just happening immediately afterwards. So the Tippecanoe sequence resulted from the rise or transgression of what we call the Tippecanoe Sea onto the craton. And so we have all this quartz sandstone over here, and that's called the St. Peter sandstone, and this is probably some of the best known of the Tippecanoe sequences. It's a very pure sandstone, and it's actually used in the manufacture of glass. So that means it's pretty much pure quartz, not much else going on. So that's a very special type of sandstone there. We're also forming a lot of reefs during this time too. So we have a lot of reef habitats extending across Missouri and elsewhere, Oklahoma as well. And that's also happening during this time because we're still in a very warm tropical climate during this time. This is a picture of kind of a present day community of a reef. So reefs are made up of coral. Remember, those are animals, and they are building all these structures during the Ordovician period, getting into the Silurian period. So while we don't have any plants or really any life at all on land, we do have a whole bunch of life in the seas, and they are building some of the most impressive structures that have ever been built on our planet, and that's reefs. And I don't want to say coral reefs. This is definitely a coral reef because this is modern day, and our reefs today are largely built from corals and sponges. But during the Ordovician, during the Silurian, they're being built by other things because there weren't a lot of corals around yet. But I've just got a couple slides at the end here about the life during this time period. So after we had that sandstone being developed from the early rising of the Tippecanoe Sea, we then get the deposition of carbonates, which, like limestone, and that's from these organisms, like some bryozoans, sponges, things that are creating limestone from creating their little exoskeletons. So as these animals die and their little bodies are tumbled around, they create limestone. So we get a whole bunch of these different organisms, again, in this tropical, very warm climate, creating reefs. Um, and then eventually, toward the eastern part of North America, we start to get these carbonates kind of grade into shales more, so we get shale. And this is actually going to be some sediment eroding away from the Appalachians. So the Taconic Highlands, very nice and high, eroding some of that clastic sediment off, and that's going to become some shale dumped on top of the carbonates during this time. So rivers during this time from the Appalachians are going west. They don't go south, no such thing as the Gulf of Mexico yet. They're heading west and actually go as far west as Arizona at one point. So what are these reefs made out of? So during this time, Ordovician, Silurian, they're made out of these kind of, they're made out of archaeocyathids, which are a type of sponge. So let me write that because I actually am kind of surprised that word's not here. Sponge. So archaeocyathids don't have anything quite like this around today, but just from the symmetry of this, the radial symmetry, like the spokes of a bike, I know that this is a sponge. Today, reef builders are corals, some algae that create their exoskeletons out of calcium carbonate. But back during the Ordovician and the Silurian, we're looking at this very ancient group, oh, I didn't mean to cross it out, very ancient group of sponges. So they're building the majority of our reefs, which is pretty cool. You know, it's really neat that, you know, we can't, when we're talking about Earth history, we can't just use the word coral reef because, gosh, even more recently, even during the time of the dinosaurs, some reefs were made out of a type of clam called a rudist. We'll deal with that later too. You know, reefs haven't always been made out of coral. Even fairly recently, they've been made out of, you know, things completely different from corals. So during the Silurian, what's going on here? Some of my favorite, well, okay, that'll be a little bit later. So again, we have a lot of reef environments and a lot of carbonates during the Silurian. So reefs often form between a shallow lagoon on the landward side, and the land during this time would have been this mountain belt forming part of the Appalachians, and the deeper water on the other side, further away from land. If the lagoon is restricted or cut off from the open sea by the reefs, then we can actually start to get evaporation of seawater. So we can get rock salt, rock gypsum, something called anhydrite. These are all very common evaporite minerals, and that's what we find around Michigan. So this is now forming the Michigan Basin as we have this lagoon somewhere between the open ocean, which is the rest of North America is the open sea, and between land, which is the Appalachians. So we're forming a lagoon, and this periodic you know, sea level rise and then complete evaporation of this lagoon, sea level rise, evaporation, and so on, is creating a lot of salt, which ends up being some economically important rocks of Michigan and the other areas of the Great Lakes. So this creates a salt basin, and that's kind of neat. So we see a lot of reef deposits elsewhere. We have these barrier reef structures, so these very large, hard ground reef structures, but then we have a bunch of salt in the middle. So I think what's kind of cool about what your textbook is doing and what I'm kind of following along with here is that we are finding, if you've heard of the Michigan Basin before, you've heard of the Grand Canyon, you've heard of the Appalachians, maybe you've heard of the Cordillera, you've heard of the Rocky Mountains at least, you've heard of these places. And now we're getting into how do these places form and how do they fit in the tapestry of Earth history. So we're kind of putting them chronological, sorta, though. They're almost all of them are formed from various events that occur, you know, in very, very different times. So the Tippecanoe Sea is finally regressing, or, you know, sea levels dropping during the late Silurian. So all those evaporite minerals, so limestone is forming as well from the reef system. But then we have rock salts, which is what this picture is of. This is a core of rock salt from the Michigan Basin. Down here, we're seeing the limestone. Oh, sorry, this is a cross-section of the reef formers. Another type of sponge called stromatoporoids. Sorry, that's a hard word to say. So we have basically a hard ground reef, we have salt, and anhydrite and a few other economically important minerals, all because we have sea level dropping. Um, all right. Okay, I think that's probably about that. Oh, just a little bit about how evaporite sedimentation occurs. So again, the sea level is dropping, and then the water is evaporating, leaving behind a crust of, we got calcite, we'll get gypsum, and finally salt. And then after burial, that gypsum mineral will dehydrate, so some water gets squeezed out of it, and it becomes something called anhydrite. So all of these sediments are pretty useful in economic purposes. Gypsum is used to make drywall. Calcite's used to make cement. Salt obviously has a lot of uses. So, very economically important. It's all because of an ancient shallow sea that evaporated away that today makes up the Michigan Basin. And by the way, when we think of Michigan, we may think of the Great Lakes and, oh, there's a lot of water there. Well, that's super, super recent. Those only formed during the last ice age, like within the last tens of thousands of years. Remember, we're talking about Silurian times, so about 400 million years ago at this point. Okay, and then finally, our Appalachians. I don't have a whole lot to say about these because we already covered the Appalachians pretty well in another lecture, so make sure to watch that. But to kind of give you a perspective as to what's happening during this time, this is where we're starting to form a divergent plate boundary, splitting apart Laurentia and Baltica. So these are passive continental margins. We're starting to drive them apart after they've collided together. And this region was a broad, very passive, no mountain belt going on during the Silurian as these divergent plate boundaries were widening and widening. So the Appalachians and any mountain belt aren't just a story of collision. They're also a story of peaceful activity and spreading happening. Remember the Wilson cycle back with the Appalachian talk. All these things are going on all the time. I like this because this is getting into the Appalachians too, but also Caledonian Highlands. This is Scotland. And down here with Avalonia, where's that? I don't know. But anyway, that's going to be England. So these guys will suture together at some point. As we know, England and Scotland are attached today. So eventually, and this is kind of what we think is going to happen off the east coast of North America in the next, 100 million years or so, is that instead of a passive continental margin, eventually that oceanic crust that's just off the east coast of North America is going to become heavy. It's already very old and dense. It's 180 million years old. It's going to become heavier and heavier and begin to sink down and begin to create a subduction zone. And then we'll have new volcanism happening again. Well, how do we know that's going to happen? Because it's happened 3 times already, So again, the Wilson cycle is the sequence of collision and mountain building, peaceful extension, and then as that crust becomes too heavy, that formed from that extending divergent plate boundary, it begins to sink back down, forming another subduction zone, and so on and so on. So that's a very cool cycle, and we're just, every mountain belt in the world, every passive plate margin in the world, whatever, are just in the midst of some part of that Wilson cycle. And I think that's really cool. Okay, so here's our Taconic Highlands. Again, this is going to be Scotland someday. And some other parts down here, some sediments that are being dumped from the erosion of the Taconic Highlands. So again, this is our Appalachians, and they're eroding off sediments like mountains do today as well. And that's going to cover a lot of this, a lot of these more ancient marine sediments in some nearshore sediments that some of them are even rivers too. So we know rivers went pretty far, extended pretty far out onto the rest of the continent. Okay, so that was pretty much it about geology. The last few slides are just about life. So I have one, just, if you take prehistoric life, you get into a lot more detail than this. But this is just one slide per geologic period, and I'll do this for the rest of the lectures as well. So life in the Cambrian. Let's put a little bit of perspective here when we're talking about plate tectonics and all this stuff. All right, what's life doing? So we stopped when we were talking about life with the Ediacaran fauna and the Burgess Shale fauna a bit. So we have the first predators showing up during the Cambrian. Don't get too excited. They're not dinosaurs or anything like that. They're things like this Anomalocaris, which is probably a crustacean relative or something like that, but they become huge. We're talking about animals that are 4, 5, 6 feet long. So the first large predator. During the Cambrian, though, most animals, really no plants, some algae, but no plants during this time. Most animals are just kind of hanging out near the sediment water interface. What does that mean? It means things are laying on the sediment, swimming just above the sediment, burrowing just under the sediment, but they're pretty close to where the sediment and the water connect. They're not really swimming very high. They're not really burrowing very deep. That's going to happen later in the Ordovician. Again, the reef builders are the archaeocyathid sponges. We have the trilobites are dominating the Cambrian and are a very important group of index fossils for the Cambrian period. We have brachiopods, so some little seashells, not really seeing any brachiopod here, but the little seashells that you see in our region, those, they show up during the Cambrian. And then echinoderms, so all sorts of things kind of related to starfish, crinoids like this guy, or sea lilies. Those are all in the echinoderm family. So they're beginning to show up and beginning to diversify. We have a few other weird forms, but not a whole lot of swimmers. Things are just kind of laying or crawling around on the floor, mostly during the Cambrian. And we have a lot of groups that are not really very well recognized. This is a guy called Wywaxia. We really don't know what that's related to. This is a guy called Hallucigenia. We don't know what that's related to. There's all sorts of life here that, may or may not be related to any animal life we have today. Okay, the Ordovician. So again, this is the age of our local rocks here in Cincinnati. This is a very cool book. Your NKU's library should have this because I had them buy a copy, called A Sea Without Fish, and I thought this was also a good picture to look at for looking at the life of the Ordovician. No fish during this time. The first jawless fish were beginning to show up during the very late Ordovician, but they really weren't top predators. The top predator, the big swimmer at the time, was this nautiloid, a long-shelled cephalopod related to today's octopus and squid. All these little branching forms here, like that guy, that's a bryozoan. All this stuff painted green, yellow, these are also bryozoans. These are colonial animals, much like corals in a way, and they are still around today. But they are forming a lot of the major reef systems of the Ordovician and make up the majority of the limestone rock that we see here in our region. This guy here, this is a brachiopod, the things that we see in our local rocks that we call seashells. They're not closely related to clams or oysters or scallops or anything like that. They are their own group, and but there are still a few of those alive today too. So that's kind of what's dominating during the Ordovician. But the big trend that we see is something called the Great Ordovician Biodiversification Event. This means that we are getting more swimmers. Life is finally moving away from that substrate-water interface. Things are burrowing deeper and deeper. Animals that are attached or stalked are growing taller and taller. Some animals are swimming higher and higher, further away from the seafloor. We don't just have things crawling around. Animals are beginning to explore a little bit more, I suppose. And finally, for the first time, the stromatolites, the major life form that we've had on our planet for a few billion years up to this point, they finally begin to decline, mostly because we're starting to get some snails. We're starting to get things like things kind of related to sea urchins, starfish. These are grazers, so they're able to eat algae. So as we get more and more animals that are eating algae, then stromatolites will continue to decline, and today we only have them in a few special areas in the world. There is a big extinction event at the end of the Ordovician from glaciers. So the very first growth of glaciers since complex life evolves on Earth happens at the end of the Ordovician, and one of the big reasons for that is Gondwana moves southward. So as those southern continents like Africa, South America, Antarctica, India is included as well, strangely enough, Australia, they all move southward. Well, now you can start to grow ice, because if you don't have a continent on a landmass, you're never going to grow, or sorry, if you don't have a continent on one of the poles, you're never going to grow ice. You need to have land mass at one or both of the poles in order to start getting glaciers to form, and that means you're starting to get sea level to drop. Well, that's what happened, and even though these animals were nice and safe and still very warm and tropical on the equator here in the Cincinnati area, they experienced a sea level drop that would cause extinction events to occur. So biggest mass extinction event since complex life evolved on Earth, and we have direct evidence for it here in the Cincinnati area, where we have fossils that date from the very late Ordovician. Okay, and then life in the Silurian. Now we're starting to get some more advanced jawless fish. We start to get the very earliest fish with jaws, and the invention of the jaw was a huge deal for these early vertebrate animals. So fish are going to eventually diversify, and during the next period, which will be the next lecture, called the Devonian, jawed fish are going to kind of take over, and you know, they're a very cool group, and everything else that every four-legged animal, every vertebrate basically that evolves after the jawed fish, from the jawed fish, are things that we care about. So amphibians, reptiles, mammals, birds. So developing that jaw, our fishy ancestors did that, and that allowed, you know, so much diversification and conquering of the planet. But before that, let's think about our invertebrates, because they're kind of driving the bus at this point. They're running the show. So clams are going to diversify, which is a big deal because today clams, you can't look at any water environment and not see clams. They're everywhere. They are one of the most successful groups of animals on the planet. What this picture is showing us, though, that's really cool, is something called a sea scorpion or a eurypterid. These are often found in like salty or kind of a mixture between salt and freshwater deposits, and maybe even some rivers too. So this is an animal that's starting to move up streams. Some of them could be up to 9 feet long. So we're talking about, you know, the largest predator up to this point. And we know that some of them were actually capable of walking around on land. So it's not really technically a sea scorpion, not that closely related to scorpions. But like all arthropods, you know, insects, crustaceans, spiders, scorpions, millipedes, centipedes, all those guys, they have the ability to to breathe outside of water and inside water. So they could, you know, often do pretty well. So that's what's going on during the Silurian. And I like this picture. I'm going to have this up on every lecture because this has, we're going all the way from Earth history, 4.5 billion years ago. And then as we finally, this is pretty cool because it is to scale. So our talk I think it is sort of to scale. No, not even close. I'm sorry, not even close. That's what this fat line is representing, is that, now we're starting to get to scale. Okay, so we started today talking about the Cambrian, the Ordovician, and the Silurian. So we talked about this part of the Phanerozoic eon, just the very early Paleozoic. Next time we're going to talk about this part. So we're going to get into our jawed fish. We're going to start to actually get plants coming to land. We're going to start to get reptiles. Then we'll get into the Mesozoic, which is the age of reptiles. And then finally, the Cenozoic. So we're not focusing on life so much in this class. We are focusing more on the geology that's going on. But if you've taken this and prehistoric life, then between the two of them, and you don't need two of them actually for a geology major, you only need to pick one. Now, as we change the curriculum on you, you only, so after this class, you've already had one class in the bed to become a geology major, right? But this is, both of them are giving a really good idea of what's going on throughout our Earth. And I can't remember all of this stuff. I can't put all this stuff in order perfectly, or even really close to perfect. It's more of an appreciation and understanding for the things that we've done. Anyone who could just memorize fact after fact after fact in chronological order, that's less impressive to me than just, if you basically feel like your mind has been blown by how much diversity of life and how much interaction, the complex interactions there are that we understand between life and the atmosphere and climate and geology and all these, nothing is an island. Everything is connected. If you're able to see that throughout geologic time as well as today, then you're in pretty good shape. And my job is somewhat done. Okay, and then these last few slides, I know you can't read too much of this, but I put all of them together. This is just kind of summarizing what's going on with life. So some special evolutionary events here, different mountain building events and other important geological events in North America. Yeah, there's our orogenies. Some of the special packages of sedimentary rock that are developing, and a lot of these have to do with sea level, so we can see how sea level is rising and falling. And then I just broke them, I just split them all up here so you can kind of see all of them. So anyway, that's all I've got today, guys. I'm going to go ahead and get the other Paleozoic one up quickly, and thanks.